Am I audible, Venkat, sir?
Yes, madam. Now you are audible. A very good evening to everyone. Welcome to the second day of our ATAL sponsored faculty development program on Outlook on Best Practice and Strategies for SIP Design and Implementation from Industry Perspective. Now, I want to introduce today's our speaker Sri K. Sujan Garu. He is technical expert manager at Enium Semiconductors, Bangalore. He is having more than 8 years of experience in semiconductor design companies. Now, I would like to address the gathering. Now, I am handing this session to Sujan sir.
Yeah, hello everyone. Very good evening.
Sir,
Hello,
good
sir.
evening, sir. Thank you for accepting our invitation, Sujan, sir.
Yeah, thank you.
Welcome to the session.
I hope everyone is able to hear my voice clearly.
Yes, sir, you are audible.
Yeah, thanks for confirmation. So, can we get started with today's discussion? Yeah, can I share my screen so that I can go through the slides? Yeah, thanks.
Sir, you can share your screens.
Ah.
Sir, you can share now.
Yeah, got it. Thank you. You're able to see my PPT.
Yes, sir.
Thank you. Yeah, I'm on screen mode. So if anyone is facing any difficulty to see it, please let me know. I'll stop sharing and again reshare it. Today I'll walk you through the concept called static timing analysis, which will come at the final stage of our chip designing process. So what is static timing analysis? Yeah, you're able to see my first slide, right?
Yes, sir.
Okay, thank you. So I would like to go through the static timing analysis concept in today's discussion.
Sir,
So
your voice is not clear, sir.
It's not clear. How about now?
Yes, sir. Okay, sir. Now it is clear.
Okay. Yeah. So static timing analysis generally is a method that we use to verify our design with respect to the timing constraint. So when discussing about the different inputs that are present in a physical design, you might have gone through about netlist, SDC, lib, left, etc. So every design when we implement it or when we thought of the architecture, right? So it will have some timing specification. Timing specification is nothing but the operating speed the design should work at a particular frequency. For example, I have designed a chip which will operate at
Sir, voice is not audible.
Sujan sir, your voice is not audible. All the participants just wait for 2 minutes. Sorry for inconvenience.
Meanwhile, dear participants, we'll share the feedback link in the chat box only. We don't want to share it in WhatsApp group. So please stay throughout the session, and at the end of the session, we'll share the feedback link.
yeah. Sorry, there's a technical issue at my end. You're able to see my presentation, I guess.
Yes, sir.
So I stopped at a point. We have designed a circuitry or a chip that our specification is that it should meet a 500 megahertz clock period, which means that
Sir, excuse me, sir. Your voice is low, sir, and it is breaking, sir.
About now, is it clear and audible?
Now it is okay, sir. Now it is okay, clear, sir.
Yes. Sorry for multiple technical issues. Yeah, sure. I think we can continue now. So we have designed a chip, maybe something for a mobile or something. So it should operate at 500 megahertz. So 500 megahertz time period will be 0.2 nanoseconds. Time period and frequency are inversely proportional, right? So what is the purpose of static timing analysis is all the circuitry or registers that are in our chip should operate within the time period or the frequency that you have designed for. Means that you have a timing. So in static timing analysis, we will be discussing about timing path. Each timing path, we have to verify our design so that it meets this timing constraint. Like the entire chip should work within this 500 megahertz range only. So that's how we design a chip, and we static timing analysis is the method to verify our design, whether it is with respect to the timing constraints that you have created, which will be in the form of SDC file. So mainly it will contains information like clock definitions and multi-cycle paths, false path, which we'll be going through in details in the coming slides. But for an overall definition of timing analysis, it is a method to verify our design, with respect to the timing constraints that we have created for a particular design. Okay, so there static timing analysis, we also have a method of a verification called dynamic timing analysis. So in dynamic timing analysis, to verify a design, our inputs keep changing at each register. Okay, like 1 and 0. So there is an input stimulus vector that you give and you verify our design. So that is called dynamic timing analysis. So static timing analysis, there won't be any input. You will take one constant input and you verify our design. So when you compare both static timing analysis and dynamic timing analysis, so static timing analysis, as it does not require any input, right? So the verification process is very fast here. Because it is not any input is not required, like logic input vectors is not required for static timing analysis, and it will check all the possible paths that are existing in a design, and this will only check for timing and not for the functionality. So these terms may be new to you, but going forward in the coming slides, I'll be telling about what is path, what is timing, and all this. Okay. And dynamic timing analysis, this can check the timing and functionality very accurate, because at each input pin, you'll be giving a set of input stimulus vectors, and we'll be verifying our design. Okay, so this is like just a high level definition of a static timing analysis. So we'll be going through in details of the static timing analysis. Okay. So in any of our physical design or VLSI flow, at each stage we'll be discussing more. First thing we'll be discussing about inputs and outputs that are required, inputs that are required for this particular stage. So now we are at STA, like static timing analysis. Different inputs to run STA will be seeing here. So one is gate level netlist, which will have the design information of our circuitry, which will contains like all the logic gates and registers, etc. Okay, delay information. Delay information is nothing but for each cell or each logic gate, there should be some delay. So the delay information will be coming from STF or lib or DB. Here it is libraries in this. Gate level netlist is nothing but the .verilog or .vg. Generally, it will be in that format. And timing constraints is nothing but the clock definitions, like the frequency that you are trying to operate for your design. So these are the main three inputs that you generally require to run static timing analysis. And we also need parasitic information. Like when we talk about netlist, we have cells and nets. So I'm taking in a notion that you already, every one of you have already basic information about what is cell, what is net, etc. So I'm taking that as a basic input that you already know, and I'm talking. So at any time, if anyone is not understanding, then please let me know. I shall clarify your queries. Okay, so yeah, gate level netlist nothing but where it contains information. Libraries is nothing but for each gate will have a delay, and what is input and what is output. That information will be present in the libraries. So design constant is nothing but SDC. We call it as in short form SDC. Will contain the clock information. SDF is nothing but delay information. We can use SDF for libraries, and sometimes we can use both. Parasitic RC is nothing but the net and the related R and C values to calculate the delay. So these are different inputs that we that are available for us. So we need some platform to run STA. So STA tool, generally Synopsys we have prime time, and Innovus from Cadence we have Tempest. So there are two STA tools available. So these are the tools. We provide all these inputs and we verify our design. So how do we verify? The output will be a timing report where we try to check whether our design is meeting the frequency that we are targeting or not. Okay, this is about the inputs and the outputs for ST. I'm going to next slide. Okay, so I'm from starting of the discussion, I'm mostly using the word called timing. So there are different types of timing checks that are performed in STA. Okay, so these are list of timing checks: setup check, hold check, recovery, removal. So these are clock gating checks and the min period, min pulse width. Yeah, so there are some design rule constraints like max capacitance, max transition, maximum fan out, and yeah, etc. So these are different checks that we perform in a prime time tool or a STA tool. Okay. When you talk about timing path is nothing but it has 2 points. The one is called a start point, and the second is called as end point. Okay. In next slide, we have a detailed image of just a moment. Yeah. So when you talk about timing path, it has 2 points. One is start point and another is end point. So start point is where we launch some data, and end point is where we capture the data. Okay. So the data is let me just see if you could see this second image, right? So this is a register. This is a second register. Okay. So when we call about a timing path, yeah. So I'm here. So I think you everyone will be having a basic idea about the register and the flip-flop, which is a storage element. So this is one register and this is second register. So the register that is sitting on this left side is launching the data, which we call as start point. And the data that is launched from this flip-flop will pass through some combinational delay, combinational logic, which is nothing but an AND gate, OR gate, buffer inverter, like very complex or maybe sometimes simple logic, and then it will reach a next register. Okay, so the next register we call it as an AND point or a capture point. So this is simply we call it as a timing path. So what we verify in a static timing analysis is, as we know that the clock is having one input pin called data, other input pin as clock. So whenever the clock changes, so in first timing, suppose we have a clock with 2 ns period. So at 0 at the edge, I have launched the data at this particular register, and at next cycle, which is nothing but 2 ns, I will go and check at this flip-flop whether the data that I have launched at this flip-flop is reaching the second flip-flop or not. So that is simply like the timing, the STA, what we do, launch data at one point and go and check in second point whether the data is reaching there in the specified time or not. So when you talk about specified time, that is nothing but clock period. So this we call as a timing path, launching data at one pin and capturing data at other pin. And we are trying to check this with a particular time period. That is the constraint called as SDC constraint or a clock period, clock frequency or clock period. So this is start point, this is end point, or else this is launch clock, launch clock, this is capture clock. These are different naming conventions that we use for a timing path. Okay, so the start point is the place in the design where a clock launches, clock edge launches the data. So that's what I have told now. And the data is propagated through combinational logic in the path. So the data will started deep in and it will go through this combination delay and it will reach the next stage flip-flop that we call as a capture point or an end point. Okay, so whatever the operations that we do on registers, so register is a clock sensitive device, right? Edge sensitive device. So whenever the clock changes, whatever the input is there at that particular instance of the time, that is captured at the output. So yeah, that is simply a timing path and what are the different points in a timing path. Okay, so if you go in detail about what is a start point of a path is a clock pin of a sequential element or possibly an input port of a design. So that I'll show in the next slide. And endpoint is the path, is a data input pin of a sequential element. Yeah. So when you talk about, so a timing path consists of not at least two points. One is launching point and other is capturing point. Okay, so what are the different types of possible launching points are a clock pin of a register can launch a data and a data pin of a flip-flop can capture the data. Okay, an input port of a design can launch a data and similar, yeah, in this is second case, input port is launching data and captured at a register input pin. Okay, so this is one more type of timing path. Okay, this is the first register timing path is the basic timing path that we most discuss. Primary input is nothing but when you talk about a design, our design will have input ports and output ports. So input port is launching the data and that is captured at data pin of a register. So that is a primary input for input to register path because this is input and this is register. This we call as input to register path. So this is one possible start point. Okay, this is one possible start point, and the clock pin of flip-flop is one more possible start point. So when we talk about end point, the data pin of a flip-flop is one possible end point. And when one flip-flop is launching data, and the data can be seen at the output port of a design. So the output port is one more and possible endpoints. Okay, so that is what this second point is talking about. Start point of path is clock pin of a sequential or possibly an input pin. So this is one possible start point and this is one possible start point. When you talk about endpoints, this is one possible endpoint and this is one possible endpoint. This is about the timing path. Okay. So whatever I told now, here it is, and all this entire thing is shown in a single image. Okay. When you talk about timing path, as I told, we need 2 points. One is launching point and other is capturing point. Okay. So here path one, yeah, in all our images, the flip-flop notation you already know. Something of this kind notation is a port. Okay, so A is an input port and Z is an output port. Okay, from this direction, A is an input port. So starts at input port and ends at data pin of a sequential. So starting at input port and ending at this is a one type of timing path. So second type of timing path is register to register timing path, where both start points and end point is a register. Okay. Yeah, when you talk about register, then the clock pin will with clock edge data will be launched. So we consider clock to data as a timing path. So this clock pin to data. So this is second path. Third path again register to output. Okay, this is register and this is output port. This is one type of timing path. Again, start point is register. So you consider clock pin as launching the data. and output port as the capturing the data. Okay. That is third type of timing path. There is one more type of timing path where there is no register is involved, because if you see fourth path, it is directly going from input port to the output port through some combinational logic. Okay, so this is the fourth type of timing path. So when I talk about timing path, I was not mentioning about this logic. Okay, so generally there will be some combinational logic between two registers, one from Q to this T. Q is output pin and D is input pin. Generally, there will be some set of combinational logics through this in this logic, combinational logic. Yeah. Hope I'm going slow, and hope I'm clear. Please note down your queries. We can discuss at last. So yeah, this is the regular timing paths. Apart from that, we have asynchronous timing path. Okay, asynchronous timing path is nothing but for a flip-flop, we generally talk about clock pin, data pin, and output pin. Apart from that, we will be having reset and clear. Okay, so when you click a reset button, everything, whatever data is there at the input of the flip-flop will get reset. Okay, so in general, that is the functionality of a reset. Okay, so reset to this input pin of this register. 3 is the input pin. So that is one type of timing path. Okay, so when I was talking about timing path, I'm telling the data that is launched at this flip-flop is captured at the next flip-flop. Okay, and it is passing through some combinational logic. Okay, so I'm telling this as data, right? I didn't tell anywhere it is clock. So this is the data. Suppose I have 0 at this at the suppose I'm taking one instance where the input pin of this flip-flop is having 0. Okay, when I give a edge to this flip-flop, then this 0 will go to the next D pin, passing through this combinational logic. So I'm talking about the data that is going from one data pin to next data pin. Okay, so this we call it as a data path, from the data that is going from output of flip-flop to input of the next flip-flop. This we call it as a data path. Okay, and every flip-flop will get a clock, right? And that clock should be connected to a clock port. Okay, the path from clock port to each input pin of a flip-flop, each clock input pin of flip-flop is called as a clock path. So this is called as a clock path. We have clock that is creating a clock and sending us the clock to each input pin. So clock path is different and data path is different. So this we need to understand here. Okay, and we also have clock gating. Clock gating is nothing but a type of power saving technique that is generally used to switch off the clock to a part of a design. Okay, so yeah, this may be, I think the details are captured. I should go through the clock gating checklist. Okay, so when I talked about combinational logic, right? Let me just tell you. Okay, so I'll just use this paint to create a you're able to see it. Okay, so this is clock path. Okay. Some other color for data. Okay, this is data D. So when I talk about combinational path, so there might be some inverter here. Okay, this data might first go to an inverter. Okay, then again it might reach an AND gate. Okay, AND gate input, one input of AND gate. Okay, then it might reach a OR gate. Okay, and finally it might reach the data pin of the next flip-flop. So this is called as this part is called as a data path. Okay, and this part is called as a clock path. So the next slide, when you're talking about the combinational logic, might contain multiple paths. Tool use the longest path to calculate the maximum delay, or shortest path to calculate the minimum delay. So in this case, I have just drawn one single path. There are no other paths possible, but there might be also other paths. And suppose the same output pin right here, it might go to one more inverter, okay, and some buffer, and let us take one more AND gate. Okay, okay, this might go to the next input pin of this OR gate. Okay, so this is simply a logic, like the RTL team, or like when you talk about architecture, they created this logic for us between these two registers. Okay, what does the static timing analysis tool does here is, so from this is, I'm calling it as a flip-flop 1, and this is calling as a flip-flop 2. Okay, from 1 to 2, now in our case there are two timing paths possible. Okay, what are the two timing paths? The path that is going like this, and it is going like this to here. Okay, that is one timing path. There will be one more timing path, which will go like this, starting from this register, this AND gate, and going through this same next input of this OR gate, and going to the next input, like register input. Okay, so here there are two different timing paths possible. I'm just taking example of two different timing paths, but there can be n number of timing paths possible for this particular register to register. Okay, when you check the timing, the STA tool will check the longest path to calculate the maximum delay. Okay, so the longest here, when you check for setup, okay, this is the longest path, right? Because it is going through multiple cells. I'm calling these as cells or gates. So one inverter, one buffer, and again one more. I think this is an AND gate I have drawn. So this is the longest path. Okay, when you check timing, the tool check timing through all these possible paths and let you know whether it is meeting your clock period requirement or not. Okay, I have drawn that image to show that a combinational logic, okay, might contain multiple paths. So to show this example, I have drawn this image. There are multiple paths between one register to register. So that is the intention of the diagram. Okay, so clock path is nothing but a path from clock input pin, okay, and that will reach the clock pin of our sequential circuit. Okay, for a design, we have more number of input pins. Among the input pins, we also have a clock pin as an input pin, which will send the clock to each register, to each clock pin of our design. Okay, so that is what we call as a clock path. Clock gating path is nothing but path from input port to a clock gating element. Clock gating element is nothing but that is used to gate the clock for our design. Okay, so that is also one type of time path. Asynchronous path, I have told you, it is nothing but reset, not the regular data. It is a reset to reset pin of our flip-flop. That is asynchronous path. Okay, yeah, this critical path, maybe I think we'll be seeing some details later. Okay. Yeah, what is insertion delay? Insertion delay, generally when you talk about the clock, till now I have drawn clock like this, right? So this is the clock port. I'm assuming that there are no delays in the clock path, and our clock is reaching each register at the same time. Okay. So what happens after clock tree synthesis is, generally tool will add buffers or inverters in the clock path. So these kind of things will happen in the PNR stage, implementation stage. During CTS process, these buffers and inverters getting added. Okay, and we see that. So if there is a buffer or inverter, then definitely there will be some delay on this cell. Okay, so then a clock won't reach our desired flip-flop at the time that you think. Okay, so it will be reaching, passing through all these cell delays. Suppose it is having some 2 PS delay each cell. So 1, 2, 3, 4, 5. After 10 PS, 5 into 2, 10 PS, the clock will reach from here to here. Okay, so that we call as the insertion delay. So this happens after clock tree synthesis. CTS is the step, we call it, in short, we call it CTS. Okay, so CTS is the delay, sorry, not insertion delay. Okay, insertion delay is the time that takes from the clock to reach from from a port to the input pin of a flip flop. Okay, so here the insertion delay is categorized into two parameters. So there is one more term called latency here. Latency is a combination of source insertion delay and network insertion delay. Okay, so why this image is divided like this is, so this box, right? This box is a partition or a hierarchy. Okay, maybe when you're talking about implementation, our entire design is divided into sub blocks or a partitions. Okay, so the PLL is the source. PLL is the point where the clock is generated. It will create a clock and it will provide it to our block input pin. Okay, the time that it takes from the clock to reach from PLL to the input pin of our block. Okay, this we call as source insertion delay. And the time that the clock is taking to reach from input pin of our block to the clock pin of a flip flop. This we call as network insertion delay. Okay, so these are different terminologies. Yeah. So what is clock uncertainty? So when you talk about latency, right? So when you talk about the clock and all, so let me go back to the image that I have drawn in the paint. So this is, there are two flip-flops in this particular design. Okay, I'm considering these two flip-flop design only our design. Okay. So this is the clock port. The clock has reached the first stage flip-flop without any cells getting added. Okay, and the second flip-flop is getting clock with, and there are some 5 cells got added in this clock path. Okay, 5 into 2, 10 PS delay. So now, what is Q? Q is nothing but the difference in the array, the difference between these two delays. Okay, from here to here, what is the delay? And from here to here, what is the delay? Now I told 5 cells, each cell taking 2 PS. So 5 into 2, 10 PS. So this is not having any cell. So I'll take it as maybe some net delay if you consider. So 1 PS if you take, okay. So this register is getting clocked in 1 PS and this register is getting clocked after 10 PS. Okay. So there is some delay difference. The clock is arriving at each of these input pins. Okay. So this difference we call it as skew. Hope you are able to follow my clock skew clock skew refers to the absolute time difference in clock signal arriving between 2 points. Okay. So I'm taking 2 points. The 2 points are this one and this one. So the clock is arriving at two different times, and there is a difference between the times. Okay. Here it is arriving at 10 PS, and here it is arriving at 1 PS. Okay. This is nothing but clock skew. So the difference between these two values is termed as clock skew. Clock skew. Uncertainty, I will come back again later. Okay. So when you talk about clock skew, yeah, when you go back again to our first slide, when I talk about start point, end point. Okay. So this is start point, right? Or a launch. So launch L, and this is capture. Okay. So the skew I am talking about is capture minus launch, right? T capture minus. Yeah, it might be written mistake here, but it should be T capture minus T launch. Okay, that we called as T skew. Okay, so when when we call it positive skew, the capture clock is late with respect to launch, then we call it as a positive skew. Okay, this is the positive skew case because the second the capture is getting clock at a later point of time than the launch, or else the delay difference between the capture and launch is positive. Okay. That is called as positive skew. Negative skew occurs when capture clock is early and with respect to the launch clock. Okay. So suppose there is one more flip flop. We call it as third flip flop. Again, it is having some inverter buffer and something. You imagine, okay? I'm just not drawing everything. Okay. So this will also get clock from our same clock. Okay. Or else assume it is getting clock like this. Okay. Now this is launch and this is capture. All right. Now this register is launching the data. This register is capturing the data. Okay. So in this case, launch flip-flop is having 1, 2, 3, 4, 5 cell delays, but capture flip-flop is only having 1, 2, 3. Okay, in this, I hope you are able to follow. So capture will be like this, going like this red color. Okay. So the capture delay is less and launch delay is more. So in this case, we get negative skew. Okay. That is the
Sir, how can we differentiate launch clock and capture clock?
Capture clock or capture point, you're saying?
Yes, sir. How can we differentiate capture point and launch point?
Okay, suppose there are, in this case, I have taken 3 registers, okay? 3 registers. 3 registers can have total of 2 timing paths. One is from 1 to 2 and other is from 2 to 3. Okay, at a time, if you are trying to check timing for one timing path, that is from 1 to 2, that time 1 will be our launch flip-flop and 2 will be our capture flip-flop. Okay, like at a time you are verifying only single timing path. I'm asking you to consider only one timing path at a time. So one timing path needs 2 registers, one to launch data and one to capture data. Okay, you have verified this timing path. Okay, now you are going to next timing path. Next timing path is nothing but the 2 will launch the data and 3 will capture the data. Okay, this is one more possible timing path. So when 2 is launching, we call 2 as a launch flip-flop or a start point. and 3 we call it as a capture flip-flop or an endpoint. So whatever that launches the data, launch, and whatever that is taking the data is called as capture. Okay, it is your interest to check from here to here or 2 to 3. Okay, did I answer your question?
Yes, sir. Yes, sir.
Yeah. Okay, so there will be one more concept called local skew. Local skew is nothing but I think you understood the definition of skew. Okay, the delay difference between the time difference between the clock reaching the two input pins on the flip-flop. Okay. When you talk about local skew, so this is one type of local skew. Okay, these two registers are related, and you are trying to check the difference of clock arrival times. Okay, this we simply call it as a local skew. But if you take, suppose I have drawn only 3 registers. There is one more register, 4, 5, 6. Okay, there are some other registers in our design. Okay, but these are all not at all related. Okay, I mean to say, when I talk about relation, there is a combinational path between these 1 and 2. There is no combinational path between 1 and 3. Okay, here I didn't draw any combinational logic between 1 and 3. So this 1 and 3 are not related. So we cannot check a timing path between 1 and 3 because 1 can launch data and only 2 can capture the data if 1 is launching. It's not that 1 is launching data and you cannot capture at 3. That is not possible. Okay, it should go by register to register only. Okay, so local skew is when you are checking the skew between 2 related registers. Okay, and global skew is nothing but when you take your entire design, what is the least latency and what is the maximum latency. What is the difference between them? So there is some 100th flip-flop in our design, and it is getting here I have drawn only 5 buffers. So it is getting 20 buffers. Or suppose it is having 20 buffers. So 20 into 2 is like 40 PS. Okay. So this is having the highest latency, and this is having the least latency, 1 PS. So 40 minus 1 will be our global skew because this 100th register and first register is not related. What you are trying to check and understand the skew. Okay. So yeah, that case we call as a global skew. Is the difference between longest and shortest branch of a clock tree. Okay, maximum insertion delay minus minimum insertion delay. So this is the minimum insertion delay 1 PS, and I am telling there are 10 buffers here. 10 into 2 is 20 PS. So this is the largest insertion delay. So this is called as a global skew. Okay. Yeah. You got the concept of skew. There will be one more concept called clock jitter. Then I'll come to uncertainty again. So jitter is nothing but a short-term variation of a signal with respect to its ideal position. Okay, so yeah, we have clock will be a square pulse. Okay, so this is 0th edge. Okay, this is first edge, and this is second. Sorry, this is the first edge. Okay, not this one. So let us consider this as 2ns. So here it will be 1, and here it will be 2. Okay. So what is jitter is nothing but this is the ideal clock. So what is ideal clock? You expect every clock pulse is like this only 0, 2, 4, 6, 8 like that. Okay, but in reality, there will be some variation in this clock pulse such that the clock will not get the next rising edge at the 2ns time period. Okay, somewhere it will be 1.8. So here might be 1.8. Okay. And if you take this case, it might be 4.5 that is named as 4.2 or 4.1. The interval is small. Okay, this is these variations can happen due to multiple parameters in our circuitry. So this is telling that the clock is not ideal in the entire case. Okay, there is some variation in the clock period. So if you are expecting that the clock period is 2ns all the time, but here it is not 2ns, it is 1.4, 1.8 ns only. Okay, because the clock edge is getting earlier. This to consider this variation, this variation is called as clock jitter. Okay, clock jitter is the short time variation of a signal with respect to its ideal position in time. So ideal position is at 2ns, but the clock is changing at 1.8 ns. This is a first simple example, and it can vary from case to case. Okay. So yeah, here it is mentioned that what are the different possible parameters that can cause this jitter. Okay, the jitter can be caused because of the factors causing jitter are the clock oscillator, and there is a supply voltage variation, temperature variation. So because of multiple parameters, this change can occur. Okay, so this variation we call as jitter. Okay, and there is one more concept called glitch. Okay, unexpected switching of any waveform is called as a glitch. Okay, so now this clock is peacefully going to its next stage. Okay, suddenly, because of some reason, there is a spike. It should not change here, but it came to 0 and again went here. Okay, this we call it as a glitch. Generally, the glitch will be very small. For your understanding, I drawn it big. Okay, there is an unexpected switching. It should be stable till the next step. It should be 0 till that next edge, but unexpectedly it is changing in the middle. Okay, this unexpected change is called as a glitch. So due to late arrival time of gate, it is a short period. Yeah, so this can clock jitter and glitch, and one more called clock skew. Okay, so these are unintentional in our design. So we don't know like how much the skew will be, and what is the jitter value, and what is the glitch value. We are unaware of that. So to make sure that we are designing a circuit that will work even though if jitter is present, even though this glitch is present. So we will add a term called uncertainty. Okay, so uncertainty includes clock skew, clock jitter, and clock margin. Because this is nothing but a safety value that you are adding or subtracting in your timing path, so that even though the clock is not reaching on time, or clock is switching between, or clock jitter is present, our circuit will work properly. Okay. To ensure that our circuit will work properly in all these possible variations, possible miscorrelations, or these things. So we include a concept of clock uncertainty in our timing path. This is just a concept, but how it is included in timing path, we shall discuss later. Skew, jitter, and the glitch. Okay. Yeah. So till now we are clear with the concepts. I shall pause for a while, and I'm ready to take questions from you.
If anybody have any questions, please unmute your mic and ask. If it is not possible, please write it in message. I will forward it. I will read it to sir.
Yeah, sure. Then we will continue our discussion. Yeah, common path of pessimism is the next concept that we are going to discuss.
Sir, what is the issues we will face if we get a clock jitter or clock askew?
So jitter is an issue, right? So
Yes,
to
sir.
make our circuit work, even though it is jitter is present, we will introduce this clock uncertainty value. Okay, so maybe I think that is not captured any of these slides. But if you look at a timing report, sorry, I could capture the details of this thing. So when you talk about the setup timing path, right? Okay, setup timing path generally okay, so yeah, let us talk about that your question here. Okay, so this is a start point, and this is an end point, or a launch, or a capture. Okay, and this is called as data path, and this is called as clock path. So these are the terms that we discussed till now. Maybe in our initial discussion, I told the data that I'm launching here at the 0th edge. Okay, I want to go and capture it in the next flip-flop in the next edge. Okay, so this time period is 20 ns now. So I'll launch data at 0th edge is 0 ns, and I'll capture the data in the capture flip-flop at 20 ns. Okay, so this is an ideal case. We are expecting that clock is arriving at 20 ns exactly. Okay, now but till now what we have seen, there is a case called the clock cannot reach. There might be some possible errors. The clock might reach early, or clock might reach late. Okay, so to ensure that even though if clock is reaching early or clock is reaching late, we use this concept called uncertainty, right? I told uncertainty is the value that will include all these parameters, and will shift our clock edge by the value that we are taking as a clock uncertainty. Suppose for 20, this 20 ns, let us consider as 20 ns. Okay, suppose if 2 ns or 1 ns is the uncertainty, then we will check the timing. Previously we used to go 0 is launch and 20 is capture, right? So I'll not capture at 20, I'll capture at 19 only, because I know there are some parameter variations. Because of that, clock can come early or clock can come late, or there might be some glitches, etc. So uncertainty is something that we'll subtract from our time period for a setup check. Did it clear your question, or is it confusing to understand?
Yes, sir. Clear, sir. Clear.
Okay, so here is here, if you see this image, this is 3 registers back to back. Okay, and one input port and one output port, and there is a clock path going like this. Okay. So this green color is one timing path, clock to this data pin. This we call as launch path. So till now I have told only about the data path and clock path, right? So data path is nothing but Q to D, and clock path is nothing but the clock pin, input pin of clock to input pin of our register. Clock port to input pin of our register. That is clock path. Okay, that is the first level understanding of the timing path. Okay, when you go further one more level, you can see that 2 more terminologies coming into the picture. One is launch path, and other is capture path. Okay, launch path is nothing but the clock path that is on the launch side, that is connecting to the launch register. Okay, this path is called launch path. And capture clock path is nothing but clock, the path that is connected to this green line, these two buffers, two green color buffers. This we call it as capture clock path. Okay, and this is data path, simple data path. Here we only have one buffer. Okay, data path. So when we talk about timing path and timing delays, so the tool will calculate. So each cell will have maximum delay and minimum delay. Okay, those max and min delays are coming from a timing library. Okay. So what happens here is the STA tool, when you talk about setup timing path, it used to consider the maximum delays in the launch path and minimum delays in the capture path. And when you talk about hold check, it will take minimum delays in the launch path and maximum delays in the capture path. But what is this clock path pessimism is? Yeah, that won't apply in the first case. When you talk about this second register to third register, it is having a common clock till one point. Okay, this is the point where it is having this clock path as common. Okay, from this, the clock is diverging to launch, and again it is diverging to capture. Okay, so this we call as a divergent point. And till here, the clock is common. Only one register, only one buffer is there. This is a common clock. So, yeah, in my previous statement, I told in launch path, in setup check, the launch path will take maximum delays. Okay, this is a maximum delay, and capture path is taking minimum delay. Okay, but at a time, this particular cell cannot have maximum delay and minimum delay in a single time. Okay, that is the third point. When a path can have either maximum or a maximum minimum delay, either that or this it should have, but not both at the same time. Okay, so that is the reason we introduced this concept called common path pessimism removal, CPPR. So STA tool, yeah, we have some switches that we can enable. So it can remove this pessimism between the launch and capture clock paths. Okay, so this technique is called common path pessimism removal. The common path is from clock to this. This is the common path. So as this is common to both launch and capture, it cannot give maximum delay and minimum delay at the same time. Okay, so we should remove that pessimism. Unnecessarily, we should not check this max and min delays. Okay, so this picture, I think I have drawn it. So we were talking about timing path, verifying a design, and many other things. Okay, so what exactly are you verifying here? Okay, when you talk about verifying, so let me okay, let me take this picture only and discuss about it. Okay, so this is D flip-flop 1. Okay, nothing but a launch flip-flop, and this is D flip-flop 2, nothing but a capture flip-flop. So this is launching the data at GA. Okay, this flip-flop 1 is launching data at GA, and flip-flop 2 is capturing the data at edge B. Okay, so let us suppose the time period of this clock is let us talk in terms of seconds. Okay, 10 seconds. Okay, for our understanding, I'm talking in seconds, but generally our timing in STA will talk in picoseconds or nanoseconds only. Okay, so I'm taking as a 10 seconds. 10 seconds as the time period. Okay, what is the timing? What is the setup check here is I'll launch data at so now let us take not 10 seconds, 10 minutes. Okay, I have launched the data currently. Now the time is 7:11. Okay, I have launched the data at 7:11 at this particular flip-flop. Okay, after 10 minutes, okay, after 10 minutes, I'll go and check at this particular flip-flop. Okay, after 10 minutes, I'll check the data. I'll be waiting at 7:21 to check whether the data that is launched at this flip-flop has passed through this combination logic and has arrived at our input pin or not. Okay, I don't want all the data that is available here or not. Okay, I'll just check at 7:21 only. After 10 minutes, I will check, because that is the time where the next clock edge will come. Okay, I'm talking about 10 minutes clock cycle. Now 7:11, 7:21, I will check in the next flip flop. Okay, the data that is launched here, it should come. It should either it can come early or it can come just before that 7:21. Okay, so that is the expectation. That is a timing check. Simply to tell in a easy way. Okay, you are launching on data and you are capturing the data in a second flip flop at some particular amount of time. Okay, hope you understood that. Okay, now the concept of setup. What if the data is not coming at 7:21? Okay, I was waiting for this data at 7:21. I was unable to find this data. Okay, and it came at 7:22, for suppose. Okay, but it is of no use because the edge is at 7:21, but the data is coming at 7:22. You cannot capture the data because the flop will work only at this raising edge. That is only at 7:21. This will work. The other times it won't work. So if the data is coming at 7:22 time, it is of no use and you cannot capture the data. You are unable to capture the data in single cycle. So that in that case, you tell that your design is not meeting your timing requirement. Okay. See, why I told that example is, yeah, now you have to we have to think about the timing check, and to verify, we are verifying our timing. Okay, we are launching data and we are capturing whether the data is coming in between these 10 minutes or not. We are checking, but data is not coming at 10 minutes. It came at 11th minute. Okay, now how much is the slack? It is 1 ns, right? 1 minute, because it is coming 1 minute late. Okay, without considering setup time, hold time, and all, I am telling for our better understanding. Okay. So in this case, we say that our design is not meeting our timing requirement and it is a violation because it is violating a rule. It is not coming less than 10 minutes and it came at 11th minute. Okay, the difference, yeah, difference between required time and arrival time is called as slack. So what is required time and arrival time? It's not captured here, but okay. Yeah. So now the example that I told now, I will give a negative slack. Okay, because the path is too slow and yeah, it should come at 7:21 p.m. but it came at 7:22 p.m. because it is slow, right? If it is faster, it would have come between in less than before 7:21 or 7:20 or anytime before 7:20. As the data is slow from this flip flop to this flip flop, it was delayed by 1 minute. Okay, negative slack implies that path is too slow. Okay, when I talk about negative slack, it is nothing but you are checking data at one time. The data is not ready by that time. It is coming late than your expectation. Okay, so that is the negative slack that we call as negative slack because it is not coming to our expectation. Okay, now what is arrival time and required time? Here, difference between arrival time and required time is called as slack. Is the statement that is written here. Okay. Yeah. So required time is nothing but our constraint, which means that 10 minutes you are trying to check. Okay. Required time. What is arrival time? That the time that data is taking when you start at 7:11, like at the pin at this edge, From here to, it should go to the output pin of the flip-flop. Okay, so there is some delay from here to here that we call as TCQ or T clock to Q. This is one delay. And again, the data should travel between the combination logic. There might be some 10, 15 or any number of cells, and it should pass through all this logic. Okay, and then it should reach our next stage input pin. Okay, so it has to pass through some great difficulties to reach our next input pin. There are some delays. So clock to Q combination, and so this is the arrival path. This is called as arrival, and required is nothing but our requirement. What is our requirement? It should reach within the time period. I am telling the time period is 10 minutes here for our understanding purpose. Okay, so the difference between the required time and arrival time is called as slack. Okay, so the required time is 10 minutes. Okay, but the arrival time is 11 minutes. Okay, here in this case, what is 10 minus 11? It is -1. So it is negative slack, right? So it is -1 is negative. So which means that the circuit is not working as according to your expectation, and the circuit is slow when you check about setup. And what should we do? The path must speed up if your whole circuit is worked at the desired speed. So our expectation is the data should reach before 10 minutes only. Right? That is the requirement. So which means that it should speed up. We should speed up this combinational circuit here. Okay, now this is called as setup timing check. Now, whatever I told here, right? This entire thing, the story that I discussed now is called as setup timing check. Launching at A and capturing at B, and checking whether the data is available at your desired time period or not. Okay, that is called a setup timing check. Now, when you talk about setup timing check, the setup time is there comes the concept of setup time. Okay, so this is an internal requirement of a flip-flop. Okay, the definition goes like this: setup time is the minimum amount of time the data should be held steady before the clock event. Okay. Let me just I'll go to paint, and for a better understanding, let me draw another. Okay, so now let me consider the current time is 7:20. Okay, see, there is this is launch, this is capture. Okay, there is some data path between this, and it is reaching our next stage flip-flop. I'm not writing the input pins in detail. This is the clock. Okay. Now, in our case, from here to here is called as arrival time, and here to here is called as required time, because this is the requirement. Okay, and this is the real how the data is arriving. Now, now the time is 7:20. I have launched the data at 7:20 here. Okay, 7:20 I launch the data, and let us suppose 5 minutes is our clock period. Okay, which means that when I check the data at 7:25 at this, because 7:25 this register will get a clock. So when you check the data at 7:25, the data that you launched here should be available here. If it is not available, then it will violate setup time. Right? It should come either before 7:25, and it should be stable. Now the setup requirement is, suppose this register is having a setup timing requirement of 1 minute. 1 minute I'm taking a setup time requirement. So according to the setup time requirement, the data should be coming before 7:25, 1 minute before 7:25, and must be stable for a minimum amount of time. What is this minimum amount of time? Is 1 minute here. So I would take like the data should be coming at 7:25 or 7:24. Okay, and it should wait for the clock. It's not clock who should wait for data. It should be the data that should be coming 1 minute before, and it should wait for the clock arrival. Okay, you know, if you study this statement again, setup time is the minimum amount of time the data should be held steady before the clock event. Okay, the clock event will happen at 7:25 here. Okay, 7:25 clock event will happen. But our expectation is the data should be coming 1 minute before, and it should be stable. It should not change here. Okay. So this minimum amount of time is called as the setup time requirement of a flip-flop. Hope I'm clear to everyone. Okay. The setup time is the minimum amount of time the data should be held steady for the clock event, so that the clock can reliably samples the data. Okay. So this is the setup time definition. Okay. Hope I'm making sense and everyone is going to follow this setup time definition. Okay, now you talked about setup time and you talked about Slack and everything. And maybe you might have understood the real definition of timing path and when you call it as Slack and all. Okay, now if the data that you are trying to check is not coming at before 7:24, then it is, you tell that it is violating setup time. Okay, so if the data is coming at after 7:24 also, it is violation only. You call it as negative slack because it is not meeting the setup time requirement of this flip-flop. Okay, now so we have many raw data available for us, which is we have many different parameters here: clock to queue, combinational, and I told about combination. I told about capture clock. Capture clock is nothing but the time period, and we also talked about the setup time. Okay, so there are many different parameters, and to combine all this, so this is the setup timing equation that will help us understand the whether that particular path is violating or meeting the setup check. Okay, if you carefully observe this launch, clock to queue, combinational. Okay, this is nothing but the this path. Launch is nothing but this small piece. Clock to queue is nothing but this piece, and combination is nothing but this piece. Okay, so this arrival time should be less than the capture clock minus the setup period. No, actually, our time period is 20 to 25 is 5 minutes. Okay, but this particular flip-flop is having a time requirement of 1 minute, right? Okay, so our required time will reduce by this time because you are expecting the data to be coming here only. So our required time will be 5 minutes minus this setup time of 1 minute. Okay, our required time is 4 minutes only here. That is nothing but T capture clock minus T setup. Okay, so whenever this this top blue color is less than this bottom red color, yeah, that is the setup requirement. That arrival should be less than the required. Then only you can say that your setup is meeting. If the arrival is greater than the required, then it will violate setup. Okay, so this is the setup timing check, and I'm not drawing any clocks here, but generally we discuss setup time in terms of clocks only. Okay, so this is a start. This is embedded drawing. Okay, so this is 720. This edge is 720, and this edge is 725. I'm drawing two clocks because this blue color clock is for launch and red color clock is for capture. I launched the data at 720. I want to capture the data at 725, but this capture clock is having a setup time requirement, so I cannot capture the data at 725. I'll capture the data 1 minute before. Okay, 724 only I'll capture. Okay, the data should be come before this, and it should be stable for this amount of time. Generally, the setup check will be shown in this edges. So this is the default setup check. Okay, which we consider only one cycle from one register to other register, which take one cycle from one register to other register. Okay, then till now we are talking about setup. There is other timing check called hold check. Hold check is nothing but yeah. Now we talked about setup time, which is the minimum amount of time data should be stable before the clock event or before the active clock edge. Okay. Now hold time is nothing but the minimum
Sir,
amount of time.
sir, excuse me, sir.
Yes, yes.
Hello,
Yeah, tell me.
sir. If negative slack came, hello, if
Yes, tell me.
negative slack came, it is not possible to decrease the delay of sequential and combinational circuit. Can we insert buffers in the capture clock?
Yes, that is also one way of meeting the setup time. Because
Okay, sir.
here two things we can do, right? Either we should decrease this side value or increase this side value, so that setup time. You are talking about this side, right side value. So you want to add a buffer here, so that the clock will come little late to our. So that you want to check little late. Yeah, that is also that is possible. That we can do. That is called as positive skew, right? Because you are adding delay in the capture path, and you want to check. You want to delay the clock to our capture. So now hold time is the minimum amount of time the data should be held steady after the clock event, so that the data is reliably sampled. So now we have seen before the clock edge, our data should be stable for some time. Similarly, after the clock edge also, we want our data to be stable for some more time. Okay, this particular requirement after the clock edge is called as the hold time requirement. Okay, so this we have to this we are ensuring that the data is captured properly without being overwritten by the next data. We want to hold the data because it is hold, right? Hold is nothing but holding the data for some amount of time. Setup is nothing but setting up the data before some amount of time. Okay. Setup, you check it before the arrival of the clock, and hold, you want to hold the data after the clock has changed and for a minimum amount of time. Okay. So it is the same thing, but the equation will vary here. And the the arrival time should be greater than or equal to the required time here. The setup constraints specify how much time is necessary for the data to be available at the input of sequential device. This is the same thing that we have discussed till now. Okay. You are expecting the data. Yeah. So if you go to the statement again, how much time it is necessary for the data to be available at the input pin of a sequential device before the clock hits that captures the data in the device. Okay. So you are discussing about you're trying to check a worst case, right? We need to check the setup will be a worst case because there might be many delays possible between this launch and capture. Okay. Here, this constraint enables a maximum delay on the data path relative to the clock path. That defines that we want to ensure that we are checking in a state where all the cells in this data path are having the maximum delay, so that we check in a condition that everything is giving the worst delay. Then we need to check the setup timing requirement. Okay. So that every cell is giving maximum delay. That is the worst case you can check. Okay. So this type of checking will ensure that will enforce a maximum delay on the data path. Okay. Because if you check the maximum delay that is possible for a particular cell, then we can ensure that this setup check is proper. Just a moment. So for setup, we'll take maximum delay of the cells in the data path, and for hold, we will take the minimum delay of each cell in the data path. So that is different for both setup and hold. So when I talk about slack, okay, the amount of time by which a violation is avoided is called the slack. Example. Yeah, this and all just explained in a image with the timing 720 and 25 like that. Okay. If a signal must reach a cell input pin no later than 8 ns and is determined to arrive at 5 ns, the slack is 3 ns. A slack of 0 ns means that constraint is just barely satisfied. A negative slack indicates a timing violation. So whenever we are talking about this data, if it is coming 724 is the time it should come. If it has come before 724 at 722, 21, 23, anytime, it is a positive slack because it is coming before our expectation. If it is coming after 724, then it is violating and we will get negative slack. Okay. So that is about the negative slack. Setup and hold checking for flip-flop. So this is the same image that we have been discussing from past 1 hour. Okay. So flip-flop 1 has launched the data and flip-flop 2 is capturing the data, right? So we are talking about 2 different flip-flops and 2 different instances for a setup check. Okay, setup check is nothing but setup launching that is happening at 7:20 is the time, and suppose 20 minutes is 7:40. Okay, like that. Okay. We are checking at the next edge. Okay, setup is checked at the next edge. You see here, setup launch edge is 0 and the capture edge is 20. And that's what we were talking till now regarding setup. Okay, so hold is nothing but hold is checked at the same edge. See, here is the hold edge because we are trying to hold the same data that we are having. We are not checking with respect to the previous data or something like that. So we want to ensure that the data that is currently existing is not overridden by the next data, so that it is checked at the same edge. Okay, so setup and hold checks. Yeah, so sometime back I told like by default the STI engine assumes that all the signals that are starting from flip-flop 1 will reach flip-flop 2 in one cycle. Okay, So there, when it performs a setup check, it verifies the data path is small enough so that data launched from flip-flop reaches within 1 cycle. So if you go back to our picture, right? Okay, so this is now, I'm not changing the time. This is 7:20. Okay, our time period is 5 minutes. This is 7:25. Okay, so by default, the tool will check in the single cycle only, 1 cycle. 1 cycle is nothing but 1 time period. Until and unless you mention that it needs to be checked in 2 cycles. Okay, so it will assume that yeah, the data will reach in 1 cycle and it will only check for that. Okay, it will check for that, and if it is not reaching, then it will show that your timing path is violating with some particular slack. Okay. So I told about this thing in the N-2 slide. Okay. So when you are talking about setup, you have some particular time period requirement. Here it is 20 ns. I'm taking ns as the unit. Okay, the longest possible delay along the data path and the shortest possible delay along the clock path between FF1 and FF2. We want to check the worst case condition to ensure that our setup is proper. Okay, to ensure that worst case condition, so we will see that as much delay as that is possible in the data path. Okay, we will take the longest possible delay. Maybe in our first example, in my paint, I think that I have closed, but there I have drawn 2 flip-flops and 2 different data paths. If you remember, one is one inverter and one it is going straight, and I have drawn one more path. It is going like this. Okay. Okay. So this 1 to 2 is having 2 different timing paths here. Okay. This is going to AND gate input, something like that I have drawn, but I couldn't replicate it now. But it is something like that only. Okay. So it is the longest path that we consider when you check a setup timing path between these 2 flip-flops. Okay. When you check setup, if you want to check setup from 1 to 2, okay, it has two possible timing paths. This is 1 and this is 2. Now I am taking this D, and this square one is the longest timing path, so that even though if that path comes through this this longest path, it should be coming before this 724 only. Okay. Yeah. So we will ensure that, yeah, this is the behavior of the tool. It takes the longest possible delay along the data path. So if there are some 2 or 3 possible timing paths, here I showed only 2. There might be 3, 4. Out of these 4, which is having the longest in the sense which is having more delay. More delay will come when it has more cells in the data path. Okay, inverter buffer, inverter again, or one more buffer. So it is having 5, 6, 7. Suppose if these many buffers are there here, so it will have more delay. Okay, we will check, ensure that this longest delay we check setup, and we ensure that this is meeting the setup, then it is fine. Okay. And when coming to the clock path, okay, and the shortest possible delay along the clock paths between FF2 and FF1. So we are checking in a case so that even though if the clock reaches early, okay, for flip-flop 2, we should not violate our setup time. Okay. So we are taking the worst cases to check the setup. Longest in the sense, even though if the data comes late, I am safe. And clock path, the shortest is nothing but even though if the clock is early, I am safe. So we have to ensure the worst case possibility for setup. So that is the definition of this: longest possible delay in data path and shortest possible delay in the clock path. This is for the setup, and hold will be the reverse. Okay, the data launched from flip-flop 2 reaches no sooner than the capture clock ends for the previous cycle. Okay, so in hold check, I told, right, it should not override the existing input So it should be stable. Okay, see, you study the second statement. This check ensures the data already existing at input of flip-flop 2 remains stable long enough after the clock edge. Okay, when the clock edge has arrived, whatever the data that is existing at this input, okay, sorry, the flip-flops input, it should be stable for a minimum amount of time. Okay, so the hold check is something that ensures that the existing data at input of flip-flop remains stable long enough after the clock edge that captures data for the previous cycle. So because it should ensure that this is the existing data. I'm not telling the new data. Okay. The existing data should be stable. So to ensure that, so we will consider. So this we are telling, right? It should be stable, right? So if when will this data change? If the data is too fast, okay. If the data is too fast or shortest possible, then this will change quickly. Okay, so we will consider the worst case here. The best case here for a hold check. So the best case for a hold check is the data is changing in a very less amount of time. The tool considers shortest possible delay along the data path, which means that you are trying to build a case where the data is changing very fastly, and the longest possible delay along the clock path, and clock path is as late as possible. This is quite opposite to the setup check. Okay, we are trying to check the worst case for setup and best case for hold check, depending on the definition of the setup and the hold. Okay, now coming to till now we are talking about only the checking. Okay, check is nothing but launching data and capturing and seeing whether data is coming as per your expectation or not. Okay, so now what if the data is not coming according to our expectation? Okay. Right, because our final goal is to ensure that all the timing paths in our design, there should not be no negative slacks. Everything should be positive slack. Positive slack is nothing but it should be inside the clock time period. Okay. Now, what is the possible ways to fix a setup timing path? Okay. Now, let me. Okay. First possible way of fixing a setup path is increase the clock period. Okay. See, when you go to this picture, I told 725 is the time that you are trying to check the data in your second flip-flop. Okay, I told maybe let us consider it is taking more time and it is not reaching it 725 and it is reaching in 726. Okay, but you are trying to check the data at 725 only. Okay, if you check at 725, it will definitely violate because the data is coming at 726. So what you can do in this case, you can expand your clock or increase the clock period so that it will check at 726 and it will not violate. Our main intention is to not violate a timing path. So this is one way. I'm telling all the possible ways, but increasing clock period is one way of fixing a setup. Okay? Increasing clock period is nothing but reducing clock frequency. Reducing clock frequency. Okay, so yeah, so this is the action. This provides more time for data to stable before the clock edge. So it will have enough time because you are not checking the data soon. Increasing the clock period is nothing but checking the data little late than the expected. So, but drawback, reduce the overall performance of the system. Okay, what is this drawback? Because while suppose you have decided to design a chip, okay, and you thought you want to design it for a particular frequency, okay, and you have designed it, and at final you thought that this particular issue has occurred and you have to relax your frequency or increase the clock period, which is nothing but indirectly you're reducing the clock frequency. you're giving up on the performance part of your design because you are running it in a less frequency. Okay, so that is a drawback. Generally, we don't prefer this method of fixing setup. Okay, this is the first method. Let us check other methods also. Okay, this is with the clock and optimize data path. Okay, improve the combinational logic or data path to reduce propagation delay. Okay, so here let us go back to our picture again. Now 7:25 or 5 minutes is the time period that you are trying to check. 5 minutes. Okay, but the data is coming in 6th minute. Okay, it is 1 minute late. So what you want to do? You have to decrease that one. You have to gain that 1 minute in each of these cells. Okay, that indirectly indicates that you have to the why that 1 minute is coming. Why the 6 minutes is coming? Suppose you have 1, 2, 3, 4, 5, 6, 7, 8. 8 cells are there in our design. Okay, this cell is nothing but this gate. Okay, this is called, I'm calling it as a cell or an instance or a gate, a different terminology. So each one will be, when you talk about gate, it will have a delay because it is some circuit which takes input and which provides output. It will have some delay. So now what is saying? Improve the combinational logic or reduce the propagation delay. We have to ensure that these cells are not giving more delay, because when we go from here to here, sometimes it might take 1 minute. In some cases, it might take 30 seconds. Okay, so suppose all these are taking 30 seconds and this is taking 1 minute. Okay, and because of this 1 minute, my 1 minute got delayed here. Okay, so what I want to do, I want to reduce this data path delay as much as possible so that our our data will reach before 7:25 only. Okay, so this is one way. Nothing but you are trying to optimize the data path or reduce the delays in the data path. So if you give this 1 minute to 30 seconds, okay, and this 30 seconds to 15 seconds, if you reduce that delay, if you are able to reduce the delay, and this is to 15 seconds and this 10 seconds. So here and there, you are gaining some. Here you gain some 30 seconds. Here you gain some 15 seconds. Okay, so the data path you are trying to improve. So cumulatively, you can get all this delay, decrease this delay, and then your data will come before 7:25. Okay, data will come here. So that is nothing but improving the combinational logic or data path to reduce the propagation delay. Okay, I told about this second method is the thing that I told. You want to decrease the delay. So there are some different type of gates that we'll have in our design. We can use this type of gates to decrease the delay. Okay, now let us discuss about the first method. Okay, reducing logic depth. When you talk about logic depth, I told here there are 1, 2, 3, 4 buffers are there. Okay, buffer is nothing but input to output connection. The signal won't change its state from 0 to 1 or 1 to 0. If it is 0, if you are giving, it will be 0 only. Okay, nothing. So if you delete these 4 buffers, okay, if you don't if you delete these 4 buffers, then this 15 PS is gone, 15 seconds is gone, this 10 seconds is gone, this 10 seconds is gone, this 10 seconds is gone. Okay, you can so what I'm trying to tell here is you can reduce the logic depth. Logic depth is nothing but number of cells in the data path. Now I just removed the buffers here. Okay, and there will be one more. Minus the number of logic gates or stages in the data path. I have previously this used to have some four cells. I have removed. At least you take 4 into 15. Each one give 15 seconds, so 60 seconds. Like 1 minute you can take out here. This is one method. That is the reducing the logic depth. I'm just giving example, but there can be other ways of doing this. Okay. Rearrange the logic, redesign the logic to minimize critical path delays. Okay. So sometimes we can do this logic restructure. We can restructure our data path. Okay. Suppose there is an AND gate and an inverter next to it. Okay. AND gate and an inverter next to it. Okay. How we can AND gate don't have that symbol. Okay. How we can restructure it? We can change it to a single cell called an AND gate, right? Okay. This circuit and this circuit will serve the same purpose. Okay. Here, redesign the logic. We are redesigning the logic so that here you are having two cell delays. This cell delay is different and this cell delay is different. Here we'll have only single cell delay. Maybe if you are adding both these cell delays, it will be less. This cell delay will be less. Suppose this is having 10 seconds and this is having 5 seconds. So cumulatively it is having 15 seconds. But this is having only 12 seconds. Okay, here we are having a benefit of 3 seconds. Okay. So we can restructure our logic. This is one simple example. There will be complex restructuring can happen. The tool can take care. Okay. That is second way. This entirely we are doing in the data path. Okay. This is data path. Now, third stage, use pipeline register. Okay. Now, let me go back to the same image again. Okay. So now here our requirement is if you launch data as 720 and it should be seen at 725. Okay, 5 minutes is there. But there is a particular case where there are some 20-30 cells in our data path. Okay, like this many number of AND gates, OR gates, many gates are there. Very complex logic, and there is a case it is not reaching at 725 and not 726. It is taking almost 729. Okay, let us take it is taking 729. Okay, instead of taking one cycle, it is taking almost 2 cycles. You are able to understand this is 725 and this is 730, which means that each time period is 5 minutes I'm taking. Here it is again one more 5 minutes. Now our intention is by default you should launch a data and you should capture data in 725 only, but it is not going at 725, it is coming at 729, which means that there is very long data path is there. Okay. Now what is pipeline register is nothing but add additional flip-flop to break down combinational path into shorter stages. So here our flip-flops are blue color. Okay, I will add one more flip-flop here. Okay, and attach this data path to here, and the output pin will attach to here. Okay, if it is having some 20 logic cells back to back, after just considering the delay and our not disturbing our functionality, I will add one pipeline register. Okay, not this is just a fix, but this is not done by STA team. Okay, I'm just giving a caution here. That is done by RTL team. This cell addition at all. But this is one type of fix because there are some 20 cells back to back, and you are breaking it to 10 cells and 10 cells. Okay. Now this is an example I'm taking. So 10 cells will give less delay only. So now the earlier you used to have only one timing path. Now you'll have two timing paths from here to here and here to here. Okay, you are breaking this entire path into two parts. That is a pipeline register. Adding an additional flip-flop to break the long combination path. You are having 20 combination cells. You are breaking it to 10, 10, and adding a register. Okay, this will also get the same clock. Okay. So reduce the delay between flip-flops, allowing each stage to make it setup. Okay, this is one way, but this has also some drawbacks because you are adding one more register, and this need to be restructure our logic a lot. Okay, we cannot simply add a register wherever we want. This is also some little complex method, and reduce clock skew. This is one more method where we want to minimize the clock skew. This is nothing but talking about the clock path from here to here and here to here. Okay. Skew is nothing but the difference between this black and this one. Okay. We want to reduce this skew so that clock reaches both these points at the same time. So that is about the setup violation fixes. Going to the next slide. So what are the fixes? Yeah, when I'm talking about hold violation, I told that the data will change very fast because of that hold violation will occur. Okay. So how do we ensure that it is not changing fast? We will add some more delay in the data path because we want to hold the data. Right? Holding the data is nothing but we want to keep it for a longer amount of time. Okay. So we will place some buffers in the data path to increase the delay. Okay. This will be like quite opposite to the setup. Setup, we want to decrease the delay in the data path. Hold is we want to increase the delay in the data path. Okay. How do we increase the delay? We can add a buffer. Okay. Buffer is nothing but in just an input to output connection. So it will add some delay if you add a buffer. Okay. Modify the critical path to include additional logic. So how we modified our logic to make our setup better. Similarly, we can modify our logic also to make our code better, like adding some more logics. The opposite of this thing we can do for code. This we have done for setup, like 2 cells to 1 cell. Okay. Now if this is 1 cell, we can change it back to 2 cell for hold, permitting a hold in a timing path. Okay, that is one type. Okay. Adjusting clock. Okay. So clock skew, we have seen that a positive clock skew and negative clock skew, right? Generally, positive clock skew will help setup, and the negative clock skew will help hold. So we can make some adjustment in the clock path so that we can achieve negative clock skew in the for a hold timing fix. Okay. And also, yeah. So there is one more other type of fix where you can use different cells. Okay. And there are some cell delays which can cell types with longer hold times or different register. This we can this can hold this can delay our data path, so it will help our hold violation fixes. Okay. Cell sizing is nothing but the same thing that we discussed for the setup, right? We want to suppose that cell is giving 1 minute of delay. We want to change it to 30 minutes, 30 seconds. So that change we generally call as cell sizing. Okay, the opposite can be done for hold. If it is giving 30 seconds, you can change it to a different cell, which can give 1 minute delay. Okay. So like that, we can use the opposite way of fixing setup here. Okay, so I'll pause for a while and let you breathe and have some water. In 8:05, we can again continue our discussion further.
Okay, sir. Okay, sir.
Okay, sir.
I'll stop sharing for a while.
Dear
Meanwhile, all of
participants, you can write your queries. At the end of the session, you can ask your queries.
మ్యామ్ గ్రూప్ ఫోటో తీసుకున్నాం ఈ లోపు.
Okay. Dear participants, to upload in the ATAL portal, we need a group photos. If possible, can you unmute your videos and will let us have a group photo.
If possible, all of you please open your camera. All of you please open your camera for 2 to 3 seconds. Then I will capture group photo. Okay, thank you. Hello.
Yeah, I think we are good to continue. Let me share back my screen.
Yes, sir.
You're able to see. We have ended our discussion at hold fixes. So at this point, we have discussed multiple times where we expect the data to be reaching in the next flip-flop only in the single clock period, single cycle. We call it as single cycle or one clock period. They're different terminologies. Okay. Yeah, but tool will consider all timing paths in a single cycle paths. Okay. Now, like sometime back, I have explained a scenario where, yeah, the data is not reaching in one cycle and it is taking almost 9 minutes, which is almost 10 minutes is a two cycles, right? One cycle is 5 minutes and two cycles is 10 minutes. Okay. So this data is almost reaching 9 minutes. It is taking 9 minutes. Okay. So this case we can use, we can apply some constraints called SDC constraints. It's a multi-cycle path. This by default it is single cycle. You are letting your STA engine know that the data between these two flip-flops, okay, the timing check between these two flip-flops should not be performed in one cycle, and it should be performed at 2 cycles. Okay, so this need to be specified in the SDC, where the clock definitions and all comes, right? Okay, so this is one case, okay, where the data is, the combination logic is so long that it takes more than 1 cycle. Okay, because of that 2 cycle, it is taking more delay, and it is almost 2 cycles. You should let the timing engine know that it is 2 cycles. So it should be specified in the SDC. So all these examples, I am taking same clock. Same clock is reaching the 2 input pins. Okay, this is the simplest way. There can be complex examples where this clock is different and this clock is different. This time period is different and this time period is different. Okay, that is next level learnings. So this is a multi-cycle path, example of a multi-cycle path. This is example of 2 cycles. There can be examples of 3 cycles, 4 cycles. Okay. This comes from the SKs. This is multi-cycle path. Yeah. So this is a half cycle path. Okay. So here, if you take launch register and capture register, or start point or end point, start point is a positive edge trigger, like flip flop. Okay. And end point is a negative edge trigger, flip flop. Yeah, negative edge symbol, bubble signal is there. And we are feeding same clock for both the flip flops. Here, what generally all the examples that we are discussing, whatever I have discussed till now, I have drawn, I have taken this edge as the launch edge and this edge as a capture edge, which means that both these registers are a positive edge triggered flip flops. Okay. Now I'm telling about a different case where launch edge is launch is positive and capture is negative edge, which means that launch will happen at positive triggering in this edge, and capture is happen at negative triggering this edge. Okay, so previously we used to have 0 to 30, like 1 full cycle is available for us for timing check. But now in this case, as the capture being a negative edge triggered flip flop, the capture edge will happen at a falling edge. Okay, so we don't have the entire full cycle, and we only have a half cycle. So this is called as a half cycle path, half cycle timing check. Okay. This need not be mentioned in the SDC, but with this flip-flop naming convention, and with this tool can understand that this is a half cycle path. Okay, but multi-cycle path should be mentioned in the SDC. This need to be specified, the third point. But this we need not specify it, because based on the flip-flop behavior itself, the tool can understand. And when I say tool, it is STA engine, or the platform where we run this timing checks and all. Okay. So this is a half cycle path. This is one more path called false path. So when I was mentioning about data path, right? Okay, data path can have multiple cells. I have drawn only AND gate, OR gate, and buffer inverter, but there can be muxes also. Mux is also a combinational cell. Okay, so so if you see the arrangement here. Yeah, the data that is launched from this flip-flop is going through the second input pin of the mux. and then it is going like this, and again it is going through the second input pin of the second mux. Okay. And there can be also other paths that can go through the first input pin of the flip-flop. Okay. So some kind of timing paths generally exist. Suppose for a mux we have this selection line. Okay. So here, if you do selection line as if the selection line is same here. Okay. If I do suppose 0, selection line is 1, then the path from here 1 to like this can go, right? Correct. Okay, so if selection line is 1. Also, if there is one more possibility that the path can go through this the other input pin of the mux. Okay. But that cannot physically, that cannot logically happen, because if you control this both the muxes with a single selection line control, for this, then the data will come from this other input pin. Okay, and then it will go like this, and it cannot go like this. Okay, so these kind of paths we need to specify the tool that you need not check this path. Okay, there will be some 1, 2, 3, 4 paths present here, but you know that they are logically not correct, or functionally they are inactive or incorrect. Okay, this is not our requirement. Like maybe we may not know, but the engineer that who designs this chip, or like who writes this logic, then he'll launching the data, and this is capturing the data. It should go to these two muxes and these two input pins. Okay, the data that, but what STA tool will do, it will check all the paths. Okay, so the paths that is coming from this first input pin need not be checked. So these kind of paths does not need not be checked. So it is waste of our time to check these kind of paths. So we will mark them as false paths. Okay. So our primary goal in STA is to analyze all the true paths, only the valid timing paths in our design. So invalid timing paths should be considered as a false path, and it will save our time for our analysis purpose. This is false path. Okay. Till now we are talking about a single clock, right? Whenever I draw a or wherever the image that we saw, it is having same connection for both the input pins of start register and endpoint. Okay, now we have two different flip-flops. Okay, and one flip-flop is getting one clock, and another flip-flop is getting a different clock. Okay, now this is two different clock domains, and there is a crossing between these two clock domains. Domain is nothing but clock 1 is one domain and clock 2 is one domain. Okay. Okay. So this CD is nothing but clock domain crossing check. Okay. So for designs with asynchronous clock domain, the CDC signal violates the setup and hold window of the receiving clock, resulting in metastability. So this particular check we need to, so if this is violating setup or hold window, then the metastability state will occur, which means that the output is unpredictable and we don't know what is the output of this receiving flip. Okay, the values will keep on changing and we cannot predict what is the correct value. Okay. So this is so these clocks have to be balanced together. This clock 1 and clock 2, they should be balanced together. And also we need to specify some max delay constraints to get these paths synchronized. Synchronized is nothing but, suppose this clock will have a different period and different edges. And suppose this is 5ns and this is some 7ns period. Okay, we cannot do a check between these 5ns and 7ns time periods. So in that cases, they'll specify some max delay constraints to get these kind of timing paths to be synchronous. That is a clock domain crossing check. So there is also a pulse width check. So these are all different type of checks, like how setup check, hold check is there. We also check pulse width check. The pulse width check, the control signals are stable for longer than one receive clock period. So generally there will be a minimum pulse width check. Okay, so every pulse in our clock path should have a minimum width. If that is not having minimum width, then we have to do some countermeasures, ensure that our clock is having a minimum pulse width. The data stability check, the data updated by transmit domain cannot be captured by the immediately following received clock gauge. I think so. At this point, I think this is not that important for us, so I would like to skip this particular data stability check. Okay, so all these slides we were talking about only registers. So register is a register or a flip-flop, which is a edge-sensitive device, which means that which changes its states when there is an active clock. Okay, but when there is a in design we might have latches as well. Where latch is a level-sensitive device, which will work only there is a positive edge. The latches will change as long as the clock pin is enabled. Okay, so in latch, so when there is a register to latch timing path, then the situation becomes a little trickier here. So the concept of time borrowing will come here. So till now, this is a register, this is getting clock, so this will change in clock only. Now we are talking about a case where register to latch is nothing but that is also one type of sequential device which will operate at the levels. If the level is high, then the data can change anytime. Okay, so in latch-based design, combinational paths can be compensated by shorter path delays in the subsequential. So let me go through the concept of time borrowing. So the technique of time borrowing, borrowing time from the shortest paths of the subsequent logic stages to the longer path is called time borrowing or time stealing. Borrow is nothing but you have some extra delay, you have some extra margin. Okay, I want to borrow it from you. Like, simple definition of borrowing is taking from some other one. Okay, taking from them, from others. Okay, here if you take this image, okay, register one is the launch edge. So generally, edges is our registers generally work on the flip-flops, work on the edges, right? Okay, and so yeah, I didn't think I have captured the diagram for time borrowing. Oh. Let me get an image for time borrowing. Just a minute. Okay, I think I'm done with this register to register timing part. I hope I can delete this existing. Okay. I'll create a new one for time borrowing. Okay, so here our start point is a latch, and this is a, so this is a latch. This is a latch. This is a register, a flip flop. Now we are performing a check between these two, latch and a register, which is having some combinational logic between them. So basically how this operates, if you give clock to latch in both register, basically in a register timing path, our expectation is you launch data here in this particular thing, here to here, and you capture data here at this particular edge. Okay. But in latch case, so the data keeps changing in this entire positive edge, right? Because latch is a edge trigger device. So how long the clock is high, the latch will keep on, the data keeps on changing here. Okay. So we don't have enough timing, enough margin here to capture the data here. Okay. Because we have already lost half cycle here. Okay. So in this case, now we will borrow the time that is there in the next subsequent logic stages. Okay. So the path that is connected next to this timing path, from there we will borrow the time. This clock is reaching here. This clock basically in a regular timing path, data will launch here and it will change and we will capture here. But in a latch case, as data can change from here or anytime the clock is high, right? But the data can change here anytime it can change. Okay, now we don't have enough time to perform this check, and this will definitely violate our setup time. Okay, so now we are taking we are borrowing the time from the next subsequent logic stages. Okay, or we are stealing the cycle of the next path to meet the timing path here. Okay, so then generally when you do this time borrowing, so it basically affects the setup time calculation, because it will slow the data arrival time. When the clocks of the launching and capturing are out of place, time borrowing is not to happen. So let me go to next slides and show in detail. So when data is launching from a positive triggered flip flop and the capture is to a negative level sensitive latch. So this is how the borrowing can happen. Now the image that I've drawn is the second case. Okay. Data is launched from latch and captured to a flip flop. Okay. Now if you see the first case, data is launching from a positive edge trigger flip flop and captured it at a negative edge trigger flip flop. Okay. Data can launch at a positive trigger flip flop is nothing but this edge only the data can launch. Okay. Now negative edge trigger and negative sensitive latch is nothing but here is the area where the data can capture from the latch. Okay. The actual setup check generally happens from here to here after one cycle. Okay. Now the setup check, the actual check will happen here because it is a negative level sensitive latch. So it can start from here. Okay. Now we will borrow the time of this interval for the next timing path to ensure that this check is not violative. Okay, so this B period of time is the time that we are borrowing here for a positive to negative edge sensitive latch check. When it is coming to launch is from negative level sensitive latch and capture is a positive. So here is the negative level sensitive latch. So here the data can start changing. Okay, and capture is a positive edge trigger flip-flop, like here. So the actual time window will be from here to here only. Okay, so B is the time borrowed from the previous stage. I think this image isn't correct. Let me cross it with my demo. Another lab.
Sir, you are not audible.
Yeah, just
Hello.
a moment.
Okay.
Just a minute. I'm just crossing the image. Yeah, so so this is the time. Yeah, this image is correct only from my checking. This is from negative to positive. This is the negative edge latch and positive edge capture. Okay, the actual setup window is here. If the data changes from here to here, but we can borrow this extra time to meet our timing check from negative to positive latch. Coming to the third case, the time both the launch and capture are positive level sensitive latches. So this is purely a latch to latch timing. Okay, data can launch here and it can capture here. Okay. But in this case, generally we check at the next stage, right? So the actual setup window is from here to here. Okay, but by using the concept of borrowing, we can use this entire positive edge and check at the same edge so that we'll meet our batch based timing. So this will be a little confusing. Maybe you can just go through the detailed material, and I think this material is already sent. Maybe you can refer again and go to this checks. Okay, so we were talking about setup check, hold check, and we have also discussed about false bar, model cycle. Yeah, setup false and everything. This we are checking on the data pin of the flip flop, right? So in our initial discussion, I told there is reset and set other input pins for a flip flop as well. Okay, so this recovery time and removal time will work on this asynchronous input pins, like reset, preset, clear, etc. So the recovery time is the minimum time that an asynchronous control input must be stable after being resetted and before the next clock transition. Okay, like how the setup time is we are checking, right? Okay, so this is the asynchronous control input must be stable After the asynchronous control input is nothing but our reset and clear like those pins. So like how we check for data pins. So this reset and these pins also the data should be stable after the clock edge is recovery and before the clock edge is removed. So this is same like this. Second one is set up and this recovery time is like hold check. But we are checking on a control pin, asynchronous control pin, not on our regular data pin. Okay. So regular data pin is like a default setup and hold check. The check that we do on asynchronous control input pins will be removal and recovery time checks. Okay. So this has to be ensured that because the asynchronous signals is not occurring at the clock edge. Okay, it should be sometime before or after the clock edge. So generally, when you get clock right, whenever you get a clock, our main intention is to capture the data that is present in at the D pin. So this asynchronous clock control input pins will do. They'll either reset the data or set or clear the data, which means that they'll set it to 1 or clear the existing data that is present on the pin. Okay, so that we have to ensure that that is not happening when the clock is present. Either it should happen before the clock is coming or after the clock has come. Okay? So that is the main intention of this recover and removal time checks. Okay, so so while doing timing analysis, right? So there is a concept called path-based analysis and graph-based analysis. Okay, path-based analysis is nothing but it will extract all the possible paths in a design. Okay, next for each path it will calculate its delay and compare it with the endpoint value. And let me bring up a graph. Okay, yeah, here if you check, this is not block based, it is path based and the graph based. Okay, let me draw it. Yeah, suppose if you take, suppose we are talking about combinational logic. So when you talk about combinational logic, it can have an AND gate, priorities AND gate, and inverter. Okay, some OR gate, and something like that. Okay, it is nothing but a connection of cells back to back with combination cells, and there can be muxes, etc. Okay, so what is path based and what is graph based here is, suppose you have this is a two input this will have two inputs, right? So there will be two arcs here present here. One is from A to Y and one is from this arc to this arc, and the other will be here to here. Okay, so generally we have two arcs here. So this arc, suppose this is A and this is B. This I am taking it as Y. Okay. So now our this you consider a register only. Okay. Now this register is connected to this B pin. This Y pin is connected to this here. Okay. Now for this particular cell, okay, in our timing path, it is going through the B pin of this particular cell arc B to Y arc, and this also B to Y arc. Okay, so when I was talking about setup time, I told like it will take the maximum delay for each cell. Okay, so now if we have in the timing library, you can see that this A2Y is having suppose 3 PS. This B2Y is having 2 PS delay. Okay. Similarly, let me consider here 1 PS, 1 PS from A to Y, and B to Y it is 2 PS. Okay. So when you talk about graph-based analysis, okay, what tool will consider is for this particular cell, what is the maximum delay out of 3 comma 2? What is the maximum delay? So it will consider 3 in GPA. GPA is graph-based analysis. So it is not considering the arc, what it is going through, and it will consider the maximum delay that this cell is offering here out of these 2 arcs. So it is 3, and 3 plus, suppose the cell delay is 1. 1 plus, out of this the maximum delay is 2. Okay, 3 plus 1 plus 2 is 6 PS. So this entire delay of this data path from here to here is 6 PS. Okay. Now, if you take PBA is path-based analysis. In path-based analysis, how the tool will calculate delay of this cell is, let me pick up another color. PBA. Okay, in PBA, the delay will be whatever the arc that is existing for this particular timing path only, that arc created delay will be only considered here. So in this particular arc, in this particular cell, it has 3 and 2, but in our timing path, we have only the arc that is related to 2 PS. So the tool will consider only 2 PS delay. 2 plus this is a buffer. So anyway, 1 PS it will get no arcs. And this is going to the B to Y. So B to Y is anyway 2 PS. Okay, so it will compute it as 5 PS. Okay. So generally GBA is pessimistic because it is taking the worst delay and it is adding some extra pessimism. Unnecessarily we are adding 1 PS here because it is taking the maximum delay of these for this cell. But PBA is accurate, but it will take more time because the tool need to identify the correct timing arc and what is the delay for this particular arc and all. Okay, so this is the difference between GBA and PBA. In graph-based, irrespective of the arc, what is the maximum delay of that cell that will consider. But in PBA, what is the arc that is passing through and the delay for that arc, that only will be considered in PBA. Okay, so this is a difference between graph-based analysis and path-based analysis. Okay, so yeah, that is it. So some paths will benefit us like this. Okay. So like this 1 PS delay is nothing but how we got this 1 PS benefit from 6 to 5. So this is 1 PS benefit we got by doing the path-based analysis here. Okay. Yeah, I think that's all we have from today's session. And I'm open to take your queries and questions.
If you are
Dear
having any
participants, you
doubts,
can raise your query.
One by one, please.
Dear participants, you can raise your queries.
Yeah, feel free to ask anything. We still have 20 minutes of time left. We can discuss on your queries. Don't hesitate, even if it is a small query. You can ask, I'll answer it. Am I missing anything in the chart here?
Sir, we are inserting, initially you told that we are inserting some blocks for insertion delay. Those will inserted as our requirement. If we need a more delay, then we have to insert that insertion element.
Yeah, so generally this thing you are talking about. Yeah, generally this is no, this entire system is related to STA, but during the PNR implementation, there is a particular step called CTS, right? Clock tree synthesis, where this clock buffers, inverters, everything gets added. Okay, this is already coming as an input to our STA. The netlist that we are having already contains this clock buffers and inverter cells. Okay, so now when you are trying to fix a setup or hold, when we are talking about setup and hold fixes, right? There we talked about clock path, reducing clock skew or improving clock skew. Nothing but we have erased our. So here we have two registers. Okay. So generally the check will happen at 720 and 725. Let us take our same example. Okay. 720 and 725 without any cells in the clock path. Okay. Now, if there are some cells in the clock path, like some buffers or inverters are present, which means that you will not get the clock at 725. Okay, you will get at suppose these 4 cells is having 25. 4 into 25 is no, let us take 4 into 15. So 60. 60 is nothing but 1 minute, like in our timing. So it will be 726. Like you will be getting clock at 726, not at 725, because of the additional delay in the clock path. So in this case, you are getting some extra 1 minute of benefit here because of these 4 cell additions in the clock path. Okay, so this we can do to fix how you asked the question when we fix the setup, right? We can add the cells in this clock path so that you can delay the clock to our capture path. We will delay the clock by 1 minute and we can get benefit here. But here we have, there is one more catch here. Okay. Now this can act as a launch and capture, this can launch data and capture will be different. Okay. Now when you are trying to add delay here, it should not affect the next timing path here. So like that's a next level concept. But here, this addition we can do from our side in STA as well. That is the answer to your question.
Okay, sir. Someone else raised your hand. Can you please ask your query?
Sir, one small question from my side.
Yeah.
What are the trade-offs to be considered while setting up this hold time, sir? Setup and hold times.
So setup and hold time generally they'll be part of the library. Okay, setup time requirement, right? So when we talked about this small window here, okay, that is a part of the library, which means that we are not modeling the setup time and the hold time requirements. Okay, that will come as a part of library, and that is an input that we generally get. So we have nothing to do with this setup time and hold time values. Okay, what is in our hand is the flop is there and the setup time is there. We have to just ensure that the data is coming before the this particular window. Okay. Did I clear your question or it is still unclear? If not, can you repeat your question again?
No, sir. My question is trade-offs, about trade-offs.
Trade-offs of particularly.
What kind of trade-offs should be considered while setting up this whole time?
Okay. So now we have so generally while fixing hold time, right? What I told for setup, we need to decrease the delay, right? And for hold, we discussed that we need to increase the delay. Okay. When you are trying to increase the delay in a data path, it will indirectly affect our setup check, because for setup we want as less delay as possible, because the data path should be fast enough. Okay. But what we are trying to do for a, suppose this particular register to register, it has a hold violation. Okay. This register to register has a hold violation. So in our hold fixes, we discussed that we will be adding hold, we will be adding buffer, add buffer to increase the delay, which means that you are adding some extra buffers here to increase the delay. You are adding some extra buffers here to increase the delay. But this will indirectly affect our setup, because setup we want as fast as possible, and for hold you are delaying it. So while taking care of hold, you should ensure that the setup, that is the setup check that is between these two flip-flops, is not violating, and it has enough margin to fix the setup violation, to fix the hold violation here. Because if you are adding delay, setup will violate, because for setup we want the data to be coming as quick as possible from here to here within the clock period. But if you are adding delay, which means that you are delaying the data path, which is a negative impact for setup. So when you are adding delay for hold, or when you are trying to do hold fixes or do something for hold, we have to ensure that it is not going to affect our existing setup on the particular on this particular thing.
Okay, sir. Thank you.
Sir, if more positive slack is there, if there is any problem?
No. More positive slack is not a problem for us. More positive slack, only negative slack is our concern. But it won't be any problem. But we can do some little trade-off here. Okay. Suppose here from this register to register, you are having, suppose, more positive slack of let us take some 2ns of more positive slack. Very high positive is that slack. Okay. This does not have any negative impact on our design, but from this we can do some recovery, and so generally more positive slack this particular timing path is having, right? So there will be some cells here. Okay, each cell will offer some delay. Okay, which means that these cells are offering the best delay, so that this is being more positive. So what we can do is we can change these cells so that this more positive can become just positive, like some 2ns to some 0.5ns or something. Okay. By doing that, we can get the benefit of area from our design, for our design. Like, I mean to say, do you know the concept of drive strength by any chance? Is it being already discussed? Okay, let me tell the concept of drive strength here. Okay, suppose drive strength is nothing but suppose we have our if we take the terminology of bike, right? You have 100cc, 200cc, 350cc like that. Okay, cc is nothing but the power here. Okay, so 100cc bike will go some with one speed, but 350cc bike will go with a higher speed. Okay, so now there might be a chance that all the cells in this particular area is with high speed, like 350cc. Because of that, we are having more positive slack here. Okay, what we can do because of this high speed cells will have more delay, more area. It will occupy more area in our chip. Okay, it is occupying more area in our chip. So now what? Nothing. We can replicate it as high speed bike will cost more. Okay, so now what we can do, instead of these high speed cells, let us replace them with the low speed cells, which will have less area. Okay, by that we can get the benefit of area in our chip. There is no negative impact, but we can create a positive impact, a positive thing from this positive slack. That is just area recovery we can do. More positive is benefit for us. No issues, no negative effects. Yeah.
Thank you, sir. Participants, if you have no queries, we can wind up today. Okay, dear Sujan sir, on behalf of our Department of ECE, I would like to extend my sincere gratitude for delivering such an excellent lecture on static time delay as a part of our FDP. Sir, first I would like to say thank you for your patience for engaging our participants for continuous 3 hours, sir. Your session was incredibly insightful and very well structured, providing a comprehensive understanding of static timing analysis. The way you broke down the complex topics such as setting time, setup time, hold time, timing constraints, and critical path analysis made the concepts much clearer to all the participants. Your expertise and engaging delivery made the lecture more both informative and interactive, sir. Thank you once again for your time, effort, and willingness to share your knowledge with us. We look forward to future opportunities to collaborate and learn from you, from your expertise, sir. Thank you once again.
Yeah, thank you everyone. Thanks for patiently listening to me. Yeah, thank you, and we can. I'm leaving for now. Thank you.
Thank you, sir. All of you can leave the session.
Thank you, dear participants. Tomorrow,